Chapter 14 in the abstract algebra series is on subgroups, and problem number 1 asks us to list all the subgroups of Z6. Well, Z6 contains the integers from 0 to 5, and remember that a subgroup is itself a group, so it must contain the identity element. The smallest subgroup is going to be the set containing the identity 0. Of course, it has the closure property because 0 plus 0 is 0. 0 acts as its own inverse. It's the identity, and of course, anytime you're working in the integers under addition, you're going to have the associative property to hold. Also, the set containing the elements 0, 2, and 4, that would constitute a group as well, and I'm only going to worry about closure. Notice that 2 plus 2 is 4. 4 is also in the set. 4 plus 2 is 0. And 4 plus 4 is 2. So we have closure there. If you look at the set containing 0 and 3, likewise, we have the closure because 3 plus 3 is 0. And 0 plus 3 is 3. 0 plus 0 is 0. And of course, Z6, being a group, is automatically a subgroup of itself. Now remember, in order to have a group, in order for a set of elements to be a group, in addition to the closure property, you do have to have the associative property to hold, which I've already said would hold because we're working with integers. You need to have an identity element. We see that 0 is included in each set, and you have to have an inverse element for each element. And of course, those also exist within each set, and I'll leave it up to you to verify. Number 2, list all the subgroups of Z7. Before we start number 2, let's go back and look at this last statement in problem number 1. The last statement says that this is a property of groups and their subgroups, the property being this. Notice that the order for Z6 is 6. Z6 contains 6 elements. And notice that the subgroups have an order of 1, 3, 2, or 6. That is a property of subgroups, meaning that the order of any subgroup must divide the order of the group itself. And if you're looking at Z7, 7 being a prime number has only 2 factors, 1 and 7. So any subgroup would have to have an order of 1 or 7. That leaves us with the identity, and that leaves us with Z7 itself. Number 3, list all the subgroups of V4. Remember, V4 is also known as the Klein-four group, and its elements are E, the identity, A, B, and C. And recall that the Klein-four group is unique because each element functions as its own inverse. And because of that, we know that we have E along the main diagonal because A star A is E, B star B is E, C star C is E, and of course E star E would be E. Since the Klein-four group has an order of 4, any subset, or any subgroup rather, would have to have an order of 1, 2, or 4. And here are the subgroups. We have the subgroup that contains the identity only, and then we have EA, EB, EC, and then finally V4 itself would function as a subgroup. Now, why would we not be able to include, let's say, EAC? Well, knowing the property that we discussed from the first 2 problems, a subgroup of order 3 would not divide a group of order 4. In other words, the order of 3 does not divide an order of 4. That would be one reason. But notice we do not have closure with EAC because if you take A and C, A star C, if you look at the table, A star C is actually B. And B is not contained in the set. Problem number 4. Which elements in Z6 generate Z6? Well, the answer to that is 1 and 5. 1 and 5 are generators for Z6. 1 is obvious, so let's look at 5. Why does 5 generate Z6? Well, if we start with 5, then that gives us one element that is in Z6. And if you add 5 to 5, you get 10, which is 4 in Z6. If you add 5 to the 4, you end up with 3. Adding 5 to 3 produces the 2. If you add 5 to the 2, you get 1. Add 5 to the 1, and that gives you 0. So if you start with 5 and you continue to add 5, you will generate Z6. Again, 1 is the obvious choice because if you add 1 to 1, you get 2. 2 plus 1 would be 3, and so on. Finally, 5 plus 1 would be 0. Number 5. Number 5 says, notice in number 1, each subgroup has closure and each element's inverse is also in the set, showing that a subset of a group has closure and inverses for all elements is sufficient to declare the subset to be a group. Notice that the union of two subgroups may not produce another subgroup. For example, if you take the set containing 0, 2, and 4, that would be a subgroup of Z6. Also, 0 and 3 is a subgroup, but the union produces 0, 2, 3, 4, which is not a subgroup. For example, if you add 4 plus 3, you get 7, which is equal to 1, and 1 is not in the set. So the union of subgroups is not necessarily a subgroup. Number 6. On number 6, we're just going to examine a structure. It does have a special name, and it will appear later in the series. But notice that if you take Z6 and you break it down to its subgroups, you would have the entire group itself. That would be in the top tier. And notice that I have listed all of the subgroups in a special way. I have 0, 2, and 4, and 0 and 3. They're on the same tier. They're on the second tier because both of these are subsets of Z6. And then I have the subgroup that contains the identity, 0. It's at the bottom because it is a subgroup of every set that is above it. It is a subgroup of every group that is above it. In other words, 0 is contained in 0, 3, and 0 is contained in Z6. Also, 0 is contained in 0, 2, 4. And I'll just leave it at that for now. And we will discuss lattices later in the series.